Hello, my dear students. I hope all of you are very fine and staying safe at home. Today we are going to discuss Ncert Class 8 Mathematics Chapter 1 Rational Number. Before going to start this chapter, we will discuss about some terms which we have already learned in the previous classes, such as natural numbers, whole numbers, integers, such like terms. So let's start.
Are natural numbers. We know that nature is the full of numbers. The numbers are coming from nature. Those are the natural numbers. Actually, the numbers which we can count. Countable numbers are the natural numbers. Set of countable numbers are natural numbers. The collection of the countable numbers. We know that the numbers of animals, numbers of men, numbers of fishes, etc. So number of some species. So the countable numbers are called the natural numbers. We know the countable numbers are starting from 1, 2, 3, 4, and it will continue to infinity. It has no end. We don't know what is the greatest number here, but we know about the smallest number, which is 1. That means the collection of countable numbers are the natural numbers. It starts from 1 and going to the infinity. So the smallest natural number must be 1. Next we are discussing about the whole numbers. Whole numbers are nothing but the numbers, natural numbers along with 0. Natural numbers we know that is starting from 1, 2, 3, 4, what we have written above. Now we also write them 1, 2, 3, 4 and so on. But if you include 0 with them, then the collection of these numbers are said to be the whole numbers. That means the smallest whole number be 0, and also we don't know what is the greatest whole number. That is, the smallest whole number is 0 and we don't know what is the greatest whole number. That is, the smallest natural number is 1 and smallest whole number is 0. Again, I am repeating the collection of countable numbers 1, 2, 3 and so on. These type of numbers are the natural numbers, and whole numbers are the natural numbers along with 0. If you include 0 with the natural numbers, then it will become the collection of whole numbers. So this is the definition. These are the definition of natural numbers and whole numbers, which we have already discussed in the previous classes. Student, apart from the natural number and whole numbers, there are also the numbers integers. What do you mean by integers? Already you have learned also. Integers are the collection of negative numbers and whole numbers. Negative numbers and whole numbers. Negative numbers means -1, -2 and ... They are the negative numbers. We know already -1, -2, -3 and so on. It will be go to the infinity and negative infinity. And the whole number you know 0, 1, 2, 3 and so on to the positive infinity. Here you see that the collections are divided in 3 parts. First of all, from here to the positive infinity, they are the natural number. We denote natural number as capital N, and this is the neutral, neither positive nor negative. This is a 0 and this is the negative numbers. Negative numbers. Negative numbers 0 and the natural numbers. This total collection is the integers. If you take from 0 to positive infinity, then it will become the whole numbers. It is denoted at the capital W. Total all over this collection, that is integer, they are denoted by capital Z. This capital Z is the collection of integers, the set of integers we say minus infinity to plus infinity. All these numbers are integers. And we denote natural numbers as capital N, we denote whole number as capital W, and we denote the set of integers capital Z. Set of integers we denote capital Z, set of whole numbers we denote W, and set of natural numbers we denote N. And the definition of integers is collection of negative numbers and whole numbers. That means negative numbers, 0, natural numbers. So this is this definition of integers and the examples. There are also some numbers which we are going to discuss now. Those are the rational numbers. Rational numbers are the numbers which can be expressed as P by Q. The numbers which can be expressed as P by Q in this form, where P and Q are integers. We know that what are the integers? P and Q are the integers, and Q not equals to 0. Q will be non-zero term. Those numbers are called the rational numbers. If we give examples, it will be very much easy to you. Suppose we are going for the example. Let us take a number. If we take a number like 0, is 0 a number which is expressed as P by Q? Yes, of course. We can express 0 as 0 by 1 or 0 by 2 or 0 by 3. All these are in the form of P by Q form, where all of them are in the form of P by Q, where P adds 0 every time, Q may be any non-zero numbers, non-zero integer. Again, if you want to take any whole number apart from 0, 1, 2, 3, everyone can be expressed as 1 by 1, 2 by 1, 3 by 1, and so on. That means all the natural numbers, that is all the whole numbers, are also the part of rational number, because those numbers can be expressed as P by Q. Every integer also the rational number. If we take minus 3, is it a rational number? Yes, of course, because minus 3 can be expressed as minus by 3 by 1, that is also in the form of P by Q. That means it is also a rational number. That is, all integers are rational number. That means the natural numbers, whole numbers, as well as integers, they are the rational number, because we can express them as P by Q form. Now let's take another example. Suppose 2 by 3. This is a rational number. Of course, it is already in P by Q form, because 2 by 3 is also in P by Q form, where P has 2, Q has 3. So they are also the P by Q form. Now I am going to tell, if I say that minus 7 by 9, is it a rational number? Of course, rational number, because it can be also represented as P by Q, where P as minus 7 and Q as 9. Both are the integer. According to the definition, the numbers which can be expressed as P by Q, where P and Q are integers and Q not equals to 0, those are the rational numbers. Now, if there be such like numbers if possible, suppose if I say 5 by 0, Is it a rational number? What do you say? What you will say? 5 by 0 can be represented as P by Q. Actually, according to the definition, PQ integers and Q not equals to 0. Here we see P as 5, it is integer, but Q as 0, it is not an integer. So we can't say that this is a rational number. P by Q form, PQ must be integer, as the same time Q not be 0. So this will be undefined, it can't be defined, so we can't say that this type of numbers having 0 as the denominator, we can't say that they are the rational number. They are not rational. 5 by 0, 6 by 0, 100 by 0, those are undefined, so those are not also the rational number. So these are the definition or the information about the rational numbers. Rational numbers are denoted by as capital Q. As capital Q, the set of rational numbers are denoted by capital Q. That means we know already what about the natural number, that is n set of natural numbers are denoted by capital N, set of whole numbers are denoted by capital W, set of integers are denoted by Z, and set of rational numbers are denoted by Q. Now we will discuss about the properties of rational numbers. Some properties of rational numbers are there. There are closure property, commutative property, and associative property and distributive property. Closure, commutative, associative, and distributive property. So we will discuss individually each of them briefly how they work. What is closure property? What are the commutative property? And what is the associative and distributive property also? We will discuss step by step. First, we will discuss on closure property. First of all, closure property there are 4 operations: addition, subtraction, multiplication, and division. First of all, in case of addition, how the closure property works or satisfy the rational number. First of all, let there be any 2 numbers, rational numbers. If we add them, the result, if there be, let's see, and if possible, this C is belongs to Q. Q means the rational numbers. If C is also the rational, then we will say that the rational numbers satisfy the closure property in case of addition, or we can say the rational numbers are closed under addition. Rational number are closed under addition, or rational number satisfy the closure property under addition. If we take some examples, then we will easily understand. Let's 2 by 5 plus 3 by 7. If we add them, then the result becomes 35. 14 plus 15, that is 29 upon 35. You see that the numbers 2 by 5 and 3 by 7, when they are added, then the result become 29 by 35. You know this is a rational number, this is also rational number, and the result becomes also rational. Rational plus rational, the result is rational. Member of the family, one member of the family, another member of the family, add them, the third member of the family. If it comes, then we can say that the rational numbers are satisfying the closure property under addition, or rational number are closed under addition. Closed because they are related closely. The member of the same family, they are related. So here also, if we add them, you get the third member. So rational plus rational equals to rational. If possible, then it holds, and obviously possible. So addition is holding the closure property of rational number. Now we are going to discuss about the subtraction, closure property of rational number under subtraction. So closure property closure property of rational number under subtraction. Subtraction. That means if there be any two numbers A and B, such that if their subtraction become C, then and C, if C is also the rational number, then we can say that the rational numbers satisfy the closure property under subtraction. If we take examples, then it will be easy to you. Suppose I am taking 5 minus 7. If we will get minus 2, I am taking as whole number because it is easy for you first. Whole numbers are also a rational number. So 5 is whole number, it's a rational number. 7 also rational number, and minus 2, the result is also rational number. If rational minus rational is equals to rational, then we say that the rational number closure under subtraction. Rational numbers are closure under subtraction. If we take P by Q form in exact, then let 7 upon 9 minus 2 upon 5. If we subtract, then the LCM of denominator 45, 35 minus 18, that is 17 upon 45. This is the result of subtraction. See here, the rational number, it is also rational numbers, result also rational number. Rational minus rational become rational, that means it is closed under subtraction. Closed under subtraction. Rational number are closed under subtraction, or rational numbers satisfy the closure property under addition. So this was the closure property under subtraction. We're cleaning this. Now we're going for the another operation, that is the multiplication. In case of multiplication, closure property, how it works. If there be any two rational number, suppose A and B, if we multiply them and if we take or get any third member or the third number, so it's also be rational, then we can say that rational numbers satisfy the closure property under addition. Let's take an example. If you take 3 into 5, it will become 15. 3 whole number as well as rational number. 5 also rational. 15 is also rational. Rational into rational equals to rational. That is, it is closure property holds for multiplication. If you take fraction, then 2 by 5, 3 by 7 is equals to 6 upon 35. That means this is a rational number into rational number is equals to rational number. Rational into rational is rational. That means it is also satisfy the closure property under multiplication. Rational numbers are satisfying the closure property under multiplication, or rational number are closed under multiplication, we can say. Again, we are going to the another operation, that is the division. Division is the another operation. Also, we will take any two rational number such that A and B. If we divide them and if we get C any numbers which also the member of a rational number, then we can say that rational number holds the closure property under division. But we have to take some examples to check it. Let 5 divided by 1, we will get 5. 16 divided by 8, we will get 2. Clearly you see that 5 rational, 1 rational, 5 rational. Rational divided by rational equals to rational. If you say 5 divided by 2 equals to 5 by 2, it is also rational. Then if it is also rational, then we can say that the rational numbers are closure under division. But if you take such examples, you will understood clearly. 5 divided by 0, what will be? It's rational, we know it is rational, but it is rational, yes or no? It is not a rational number because it is not in the P by Q form according to the definition of the rational number, where P, Q are integer but Q not equals to 0. Here P and Q are integer, it is right, but Q is not equals to 0. It should be not 0, non-zero, but here 0 there. So we can't say this is belongs to Q. It is does not belongs to Q. Q means rational number, so it is not a rational number. So that means we are saying that this closure property is failure for division in case of rational numbers, because rational divided by rational is every time not clicking equals to rational number. In case of 0, when we are dividing to any number, then we are not getting any rational numbers, it is undefined. So we are saying that rational numbers are not closure under division. Rational numbers are not closure under division. In case of division, we will not say that they are closure. So I think the first property we have understood. Now we are going to discuss on commutative property under addition. Rational numbers are commutative or not under addition. So what about the commutative property under addition? Let's start. If there be any two rational numbers such as A and B, if we add them and the results of them, if B plus A in this order, if we add A plus B, and if the sum of them can be arranged in this order, that B plus A, if we change the order or change the sequence, then the result be same, then we can say that rational numbers be commutative under addition. Rational numbers are commutative under addition. Let's take some examples. Suppose 3 plus 5. What is equals to? We know that is equals to 8. And this 8 also can be arranged in this order: 5 plus 3. 5 plus 3. Here we see that a plus b and b plus a, both the results give the same result, that is 8. So we can say that these are actually whole number. Whole number and rational numbers are a whole number also are the rational numbers. So it is says that the rational numbers are commutative under addition. If you want to take in fractional form, 3 by 5 plus 7 by 9 is equals to 9 5s 45, 27, 35, and plus 5 7 40 12, 35 and 6 upon 45. So 62 upon 45. If I change this sequence, then it will be 7 by 9 plus 3 by 5 is equals to, also in this manner, the 35 plus 27 by 45, and the result becomes 62 by 45. So here we see that both the results gives same. If we change the sequence, a plus b and b plus a, both the gives the same results. So that's why we say that the rational numbers are commutative under addition. Rational numbers are commutative under addition. In case of subtraction, will it be satisfied or not? So let's check. In case of subtraction, suppose a and b both are the rational numbers, and if we subtract b from a, if it will be equals to b minus a, if we change the sequence, sign will be the same. A minus b equals to b minus a if possible. Then we say that rational numbers are commutative under subtraction. Let's check by giving an example. 5 minus 3 equals to 2. But if we change this order, 3 minus 5, will it be equal? No. It is giving minus 2. It is 2 and it is giving minus 2. That means a minus b and b minus a, they are not equal. If we take any fractional form, 2 by 3 minus 1 by 5. So the result gives 15, 10 minus 3, 7 by 15. If we change this sequence, 1 by 5 by 2 by 3 equals to 15, 3 minus 10 equals to minus 7 by 15. See here, both the results are giving different. One is 7 by 15, another one is minus 7 by 15. That is, they are not equal. So in this case, we say that a minus b not equals to b minus a for the rational numbers. So that's why commutativity under subtraction is not satisfying for rational numbers. That means rational numbers are not commutative under subtraction. So I think it is clear. Now we are going to discuss about the commutative property under multiplication of rational numbers. So let's any two rational numbers such as a and b, if we multiply them, a into b it will be, and the product, if possible, can be expressed as b cross a. A cross b is equals to b cross a, where a and b are the rational numbers. If possible they are equal, then we can say that the rational numbers are commutative under multiplication. This is the commutativity of rational numbers. So take some examples. Suppose 2 into 3. Very simple example. If we express it 3 into 2, then it is okay. 2 into 3 is equals to 6. 3 into 2 is equal to 6. Both the results are giving 6. That means they are equal. So that's why this A into B and B into A are satisfying here. If you take any negative integer, minus 2, so here it will be minus 2. So results become minus 6 and minus 6. No change, they are equal. So when we are multiplying any two rational numbers in any order, then the product of them will be equal also in its reverse order. When we change the order, then also the product be equal. If you take any fractional numbers 2 upon 3 into 5 upon 7, the results become 5 2s are 10, 7 3s are 21. So this 10 upon 21 and 5 by 7 into 2 by 3, if I change the order, then the product remains same. So that's why we consider A cross B is equals to B cross A. When we are multiplying any two rational numbers in a order, then the product B also equals to the product of them when we are changing its order in the reverse order. So that's why we can say that the rational numbers are commutative under multiplication. Rational numbers are commutative under multiplication. You can take any more examples to satisfy this A cross B into equals to B cross A. After this, we are going to discuss on the commutative property under division. So let's see here. In case of division operation, so in case of division, let's take any two rational numbers such as A and B. If we divide them, A divided by B, if possible B divided by A, that means if we change the order, that is according to the rules of commutative property, then must be equal. But let's see for division, either it is satisfying or not. So let's take any examples. 2 divided by 5. So the result is giving 5 by 2. If we change the order, 5 divided by 2, is it equal or not? 1 minute. So, sorry, 2 divided by 5, so it will be 2 by 5. And if I change the order, 5 divided by 2, 5 by 2. So let's see here. This is the 5 by 2 and this is the 2 by 5. Both the results are not equal. They are not equal. So we are taking another one fractional example. Suppose 2 upon 3 is divided by 7 upon 13. So let's see here. 2 by 3 into 7 upon 13 will be 13 upon 7. So 26, 21. If we change the order, 7 by 13 divided by 2 by 3. So then it will become 7 upon 13 into 3 by 2. So 7 3 is 21 upon 26. So here we see that 26 by 21 and here 21 by 26, that where both are not equal, they are not equal. They are not equal. Here also they are not equal. So that means we can't say that A divided by B not equals to B divided by A. If we take any negative numbers also, then we will see the same situation. Both the results will give the different result. That means we are saying that rational numbers are not commutative. They are not commutative under division operation. Under division, in case of division, they are not commutative, because if we divide a rational numbers by any rational numbers, the result will not be equal to the reverse if we change their order. So it's not satisfying this. So rational numbers are not commutative under division. So we have to keep in mind. So after this, we will discuss about the associative property in the another unit. So let's see for the next one.